Hi everyone, thanks for being here. And today I'm presenting our work, which is HadaSmileNet, and it's on automatic genuine smile recognition using a really interesting but simple fusion approach. This is the joint work with my professors Nabeel Mohammed and Shafin Rahman from North South University, and my thesis supervisor, Professor Philipp Koehn from Johns Hopkins University. So let's dive in. Why do we even care about distinguishing genuine from posed smiles? Well, if you look at these three expressions here, the differences are actually really subtle. The neutral face is kind of obvious, but for the posed versus genuine smile, it's not so easy to tell just by looking. But this distinction matters a lot. For example, in fields such as human computer interaction, we want systems that understand authentic emotional responses. In healthcare or psychology, genuine effect is linked to patient outcomes. And in social computing, detecting authenticity helps with things like sentiment analysis and engagement metrics. So the challenge is, how do we teach machines to catch these really subtle cues? So, what have people tried before to address this specific problem? Well, previous approaches fall into two basic camps, which is before and after deep learning. Pre deep learning methods calculated features manually from facial landmarks using facial action units and landmark points. These features are usually called the Duchenne markers or D markers. And these are features such as position, speed, and acceleration of the facial landmark points. For the deep learning based approaches, on one hand, we have methods that completely ignore physiological cues. They just throw deep learning at the problem, end to end from raw input videos to classification, which works okay, but you're missing out on decades of psychology research about what makes smiles genuine. On the other hand, a very recent method from 2024 do incorporate these cues, but they use a multitask learning pipeline. And if you've worked with multitask learning before, you know that it adds all these complexities, such as you're balancing multiple loss functions, you're having to do hyperparameter searches, uh, you have multiple classification heads, you get unstable gradients, so on and so forth. Also, the model size becomes larger and the training or inference becomes slow as well. Overall, it's just really finicky to train, and as a result, we wanted something better and something gets the best of both the worlds. So, what have people tried before? Let me zoom in a bit on what these demarkers actually are. So, we're tracking the facial action units 6 and 12, which are the orbicularis oculi muscle, which is the muscle that creates crow's feet around our eyes, and the action unit 12, which is the zygomatic major, which pulls the corners of our mouth up. The key insight from psychology is that genuine smiles activate both these muscles, but posed smiles often skip the eyes. And as a result, from these action units, we can extract different marker types. And here we've got duration based features such as how long does the smile last, amplitude features, which describes how intense the movement of the muscle is, and also the speed and acceleration, how quickly does the smile develop, so on and so forth. And there are also these ratios between different measurements, and all of these captures the temporal dynamics of the smiles, because genuine smiles have this characteristic timing that posed ones don't quite replicate. So these are good differentiators between genuine and posed smiles. So here's our approach. Uh, we start with a transformer that extracts deep features from the video frames. This captures all the high level visual patterns, and at the same time, we compute the demarkers. And here's the key innovation: instead of doing multitask learning or complicated attention mechanisms, we use Hadamard fusion, which is just a fancy way of saying element wise multiplication between the two feature spaces. This approach is parameter free, it's super simple, but it acts like a gating mechanism where the handcrafted cues help focus the deep features on what actually matters. And then we simply pass this through a classifier to predict genuine versus posed smiles. The beauty here is during inference, we actually drop the demarkers so that it's fully end to end once we have trained it, and we do not have to use additional manual feature extraction during the testing phase. Now, you might be wondering why Hadamard fusion specifically? We could have used any other fusion methods as well. And you're not wrong. We actually tested 15 different fusion strategies, both individual and hybrid. And as you can see here, all Hadamard based methods dominate the results. Here, one thing to mention is that the cross size is proportional to the accuracy. Therefore, with this cross, we're representing approximately 85% accuracy, and this one is a perfect 100%. Interestingly, Hadamard fusion alone outperforms all the others, even in hybrid modes. This beats concatenation, bilinear pooling, attention mechanisms, all of it. And I think the reason is multiplication naturally creates this soft gating effect where when a demarker is strong, it amplifies that part of the feature. And when it's weak, it suppresses it. It's doing feature selection, but in a continuous, differentiable way. So, how does our method actually perform uh, when compared to previous benchmarks? So, here are our main results across four benchmark datasets, which is MMI, SPOS, BBC, and the UVA NEMO. These are basically smile databases under different light settings, under different resolutions and number of frames, so on and so forth. And the first bars here that we see are the best performing traditional method from Wu et al. Then we have got the vanilla vision transformer, the mesh SmileNet, which is the previous state of the art in deep learning only. And as mentioned before, we have deep marker net, which combines the two paradigms using multitask learning approach. Lastly, we have our method, which is HadaSmileNet in purple here. So we achieve state of the art on 3 out of the 4 datasets, as you can see. On the SPOS and BBC, the improvements are statistically significant with p-values less than 0.001. And we also have 0.8% improvement on the MMI, 0.7% on the SPOS, and 1.3% on the BBC dataset. On UV and NEMO, we are competitive but not quite the best. And that's actually a fully spontaneous dataset, so it's particularly challenging. However, we do achieve state of the art on all the end to end deep learning based methods. And overall, we can see that the results are quite strong. One way to understand why this fusion technique works better is to look at the feature space representations. So this is a TSNE visualization of the previous state-of-the-art deep learning-based method on the UV and EMO dataset, where we don't use demarkers. As you can see here, there are noticeable overlaps and confusions in the feature space. And for the multitask learning approach, we get a better separation, but still there are noticeable overlaps. And lastly, for our approach, we can see how well the genuine and posed samples separate. The fusion approach gives a much clearer clustering with lesser wrong classifications, and the decision boundary becomes more obvious as well. This tells us that the Hadamard operation is genuinely creating better representations while reducing parameters or capacity. We also did a bunch of ablation studies to understand what's driving this performance. First, we look at which demarkers matter the most. Duration based features are by far the most important, as you can see here. And this actually makes sense because genuine smiles have this characteristic timing, which is that they develop more slowly, more genuinely, and last longer than the posed smiles. Second, in terms of facial regions, the cheeks and eye areas are most discriminative, which aligns perfectly with previous psychology research. And we saw that it's all about the orbicularis oculi muscle and the zygomatic muscle. Finally, our fusion helps every backbone that we tested. We tested it on two transformer backbones, which are previous state of the arts, Mesh SmileNet and Real SmileNet, and we get consistent gains, as you can see from here. So this is a pretty generalizable technique across backbones and setups. Another really important thing is that if this method generalizes across datasets, because in the real world, we're not always testing on the same distribution that we trained on. So we did some cross dataset experiments, which is where we trained on one dataset and tested on the others. And our method consistently outperforms previous state of the art in these transfer scenarios. We trained on the UV and EMO dataset since that's the largest one and tested on other three. Our method yields 1.5 percentage better on BBC, 0.2 on MMI, and 1.4 on the SPOS dataset. This suggests that Hadamard fusion is learning more robust features, which is probably because it's forcing the network to align with physiological priors rather than just overfitting to the dataset specific quirks. Now, let's talk about some practical considerations. First, we've got 26% fewer parameters than current state of the art because we're not doing multitask learning. We don't separate the prediction heads, and as a result, we're getting less number of parameters and a smaller model size. Secondly, the training is much simpler. You don't have to tune the loss weights or deal with the competing gradients. It's just standard classification. And lastly, here's the cool part, which is that at the inference time, we don't even need the demarkers. The model has already learned to use them during training, but then we can drop that entire branch so that the deployment is just a single forward pass through the transformer. This makes it way more practical for real applications. Of course, we should talk about some limitations. There are important privacy considerations here. So we are analyzing facial expressions, which is sensitive data. So any deployment needs proper consent and data governance. There's also fairness concerns. We need to make sure that these models work equally well across different demographics. Different cultures express emotion differently, so we have to take that into consideration. And there's also ecological validity and robustness of the models. As we've mentioned, lab datasets might not fully capture real world spontaneous expressions, so we need to be careful about generalization claims. And these are all the things that we're thinking about for future work. So let me wrap this up quickly. The problem that we tackled here today is that prior work either ignores physiological cues or adds complexities such as multitask learning pipelines into the problem of genuine smile recognition. Our solution is a parameter free Hadamard fusion combining transformer features with physiologically grounded demarkers during training. And then for efficiency and real world applicability, we drop these demarkers at test time or inference. And doing so, we achieved state of the art performance on 3 out of the 4 datasets with statistically significant improvements and consistent gains over the previous best methods. We also beat state of the art on all 4 out of 4 datasets based on deep learning based methods. And practically speaking, we've got fewer parameters, faster training, and better cross domain transfer. So I think this is a really compelling approach that balances theoretical motivation with practical benefits. And yeah, that's it. Thank you all for listening. And if you want to check out the full paper or get in touch, the information's right here. You can just scan it. And yeah, thanks again.